Hey yo, it's me, Frank, the function fighter, talking to you about functions and the vertical line test. Now here's a question. How do you make fruit punch? You give it boxing lessons!
First vocabulary term is an independent variable. It's a variable, often x, that represents a quantity that is being manipulated. So in this section, we're going to talk about independent variables and dependent variables. An independent variable is something that we are going to manipulate. And in this section, it's likely going to be either x or t for time. So in an equation, what happens? We usually have that equation solved for one variable. What we do is we're going to plug in a value for x. And when we plug in something for x, we then simplify this side over here and we get a value for y. And you can see that y depends on whatever we plug in for x, meaning that as we plug in different things for x, we get different values for y. So y is something called our dependent variable, whereas x, in this case, is our independent variable because we are plugging in values for x and getting values for y. Here in our table, the left column is usually going to be your independent variable, whereas the right column is usually going to be your dependent variable. In a graph, the independent variable is usually your x-axis here. Now, the dependent variable, we kind of just mentioned this. The dependent variable is a variable, often y, that represents a quantity that depends on or is affected by the independent variable. So here you can see we have our equation solved for y. And what happens is we're going to plug in something for our independent variable, x. Then we simplify this expression right here, and we get what y is equal to. Now, y depends on whatever we plug in for x. Therefore, y is called the dependent variable in this case. And when we have a table, it's usually the right side, the right column is going to be your dependent variable. And on a graph, the y-axis is usually going to be your dependent variable. An ordered pair. It's the coordinates of a point in the plane. So they're usually denoted by an x value and a y value. And here you can see in between two parentheses, we have a 7, -2. The 7 represents the x coordinate, whereas -2 is going to be our y coordinate. This tells you where to plot a certain point on the coordinate plane. A relation is going to be a set of ordered pairs. So when you have multiple ordered pairs that we're going to graph on the same graph, that would be called a relation. Next, the domain is going to be the set of all x coordinates of the ordered pairs of a relation. So here you can see we have this relation, the set of ordered pairs. And what we're going to do, it says given the relation 8, 1, -1, 2, and -5, -6, state the domain. Well, the domain, again, is just the set of all the x coordinates of the ordered pairs. So when we state the domain, it's just going to be 8, -1, -5. And that would be the domain of this relation. Now, one thing I'd like you to keep in mind is that when you graph something, the domain is going to be represented by all the elements on the x-axis, the horizontal axis. Now, the range is going to be the set of all y coordinates of the ordered pairs of a relation. So here we can see, given the relation, and we have the same relation as before, we have the same set of ordered pairs, state the range. Now, this is going to be all the set of y coordinates. So 1, 2, -6. That's going to be your range. And again, if you're thinking about a graph with an x-axis and a y-axis, the y-axis is going to represent all the elements of your range. Now, a function is going to be a relation or a rule in which each element of the domain is paired with exactly one element of the range. Now, if we look at these examples down here, the first one says the relation 8, 1, -4, 1, and -5, -6 is a function because each x coordinate is paired with only one y coordinate. Each x coordinate is paired with only one y coordinate. Now, you can see that the 8 is paired with the 1 and the -4 is also paired with the 1. That's okay, as long as you don't have one x value paired with multiple y values. Now, the second one over here, the relation 7, 2, -2, 3, and 7, -6 is not a function because 7 is paired with more than one y coordinate. You see how we have 7 paired with the 2 and 7 paired with the -6? The reason why that is not a function is because we have one x value paired with multiple y values. You're allowed to have one y value paired with multiple x values, just not one x value paired with multiple y values. Now, a function rule is a relationship between input and output values. To find the function rule, we have to observe the given data carefully and find how input and output values are related to each other. So here you can see our input values for each of these equations would be x here, a here, c here, and x here. Those would be values that we plug in numbers for, our independent variables, our input values. We're going to get out our output values, our dependent variables. So that would be y, b, y, and w. Those represent our output values or our dependent variables. Now, in terms of linear and nonlinear functions, we're going to talk about this in a second, but I want you to note, looking at the function rule, a linear function, those independent variables have an exponent of 1, x to the first power, a to the first power. That's for a linear function. For nonlinear functions, you're going to have exponents that are not equal to 1 for your given independent variables. Here, our independent variable c has an exponent of 2. Here, x is actually our exponent in this case. Both of these represent nonlinear functions, meaning that their graphs would not be straight lines. These graphs would be curves, whereas the graphs of these function rules would be lines. Linear and nonlinear functions. So a linear function is a function whose graph is a non-vertical line or part of a line. On the flip side, a nonlinear function is a function whose graph is not a line or part of a line. So here you can see a linear function forms a line when you graph it, whereas nonlinear functions do not form straight lines. They form V's or curves. Now, the vertical line test for a function says in order to determine whether a graph is a function, you're going to move a vertical straight edge across a graph from left to right. If the graph line intersects the vertical line at 2 or more points at any given time, the graph is not a function. So here's what we're going to do. We're going to test this graph right here. Is this curve a function? Well, we're going to take a vertical straight edge. Doesn't matter what it is. You can use a pencil or pen. I'm going to use this line right here. And I'm going to move it across the graph from left to right, keeping it vertical. If I hit 2 points on the graph at the exact same time on my vertical line, then it's not a function, because that would mean that an x value is repeating. So let's move it across and beep, 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 beep. Yes, we have 2 points here, we have 2 points here, we have an infinite amount of 2 points, right? Because the vertical line intersects the graph at 2 points at the same time, the graph is not a function. And I could have picked a number of points for this one. Here, doing the same thing, I take a vertical line and I'm going to move it across the graph from left to right. And do I ever hit 2 points at the same time on my vertical line? No, I don't. Therefore, this is going to be a function. What about here? Let's take our vertical line and we're going to move it across this relation, this set of ordered pairs. If I move it across, beep, I hit 2 points at the same time, meaning both of these points have an x value of 3. Therefore, this is not going to be a function. It does not pass the vertical line test.
What was Bruce Lee's favorite kind of drink? Water! It's example time.
Now, example 1 says graph the relation shown by each table. Determine whether it's a function and if it's linear or nonlinear. So let's graph each point first. Remember, these in the table are just ordered pairs. I'm going to graph -2, 0 first. So I go over -2 on my x-axis, up or down 0. So I put a point right there. -1, 3. I'm going to go over -1 on my x-axis, up 3 on my y-axis, put a point. 0, 6. I'm going to go over 0 on my x-axis, up 6 on my y-axis, put a point. And then 1, 9. I go over 1 on my x-axis, up 9 on my y-axis, put a point. Now, let's determine, is this a function? To do that, we're going to use the vertical line test. Now, remember the vertical line test, we're going to move across the graph from left to right with our vertical straight edge. If our vertical line hits 2 points at the exact same time on this graph, then it's not going to be a function. So let's go ahead and do it. We're going to move it across the graph from left to right, and no, we never hit 2 points at the same time. And that makes sense because we never had any x values that repeated. So we're good. This is a function. Now, is it linear or nonlinear? Well, if I were to draw a line through these points, it looks like it's going to be linear. Well, let's check with our table. As x is increasing by 1 each time, x is increasing by the same increment each time, y should also increase by the same increment. So y is increasing by 3, and then by 3, and then by 3. Cool, that checks out. Because x is increasing by the same increment, and y is also increasing by the same increment, it is going to be linear.
Adrian! Adrian! You try!
Okay, so again, with the t-table, we're just graphing each of these points first. It's an ordered pair, 0, -1. So I go over 0 on my x-axis, down -1 on my y-axis, put a point. 1, 1, I go over 1 on my x-axis, up 1 on my y-axis, put a point. 2, 4, I go over 2 on my x-axis, up 4 on my y-axis, put a point. And then 3, 8, I go over 3 on my x-axis, up 8 on my y-axis, put a point. Sweet, I have graphed these points. Now I have to decide, is this a function? Well, does it pass the vertical line test? I'm going to take a vertical line, I'm going to move it across the graph going from left to right and see if any of these points intersect my line at the same time. I need 2 points to intersect at the same time to not be a function. So if I move it across, no, it never intersects 2 points at the exact same time. Therefore, this is going to be a function. Now, is it linear or nonlinear? Looking at my graph, it kind of looks like I could draw a line through this, but it looks like it might be a little crooked line. So let's check. Is this linear? Well, x is increasing by 1 each time, so that's the same increment, so that's okay. Does y then increase by the same increment as x increases by 1? Well, y is increasing from -1 to 1, so that would be 2. And then an increase of 3, and then an increase of 4, okay? Because y is not increasing by the same amount each time as x is increasing by the same amount, then you could say that this is a non-linear function. Now, example 2 says determine whether the table, relation, and graph below represent a function. If so, determine whether it is a linear or nonlinear function. So for our table, are there any x values that repeat? No, therefore it is a function. Next, is it linear or nonlinear? Well, x is increasing by 1 each time. So as x increases by the same amount, does y also increase or decrease by the same amount? So from 7 to 5, it's decreasing by 2. In order to be a linear function, it would have to go from 7 to 5, and then from 5 to 3. Because it's not decreasing by 2 each time, it would be a non-linear function. Here, do we have any x values that repeat? No. Therefore, it is a function. Next, is it linear or non-linear? Well, you can see our x coordinate, our x value, is decreasing by 4 each time. Okay, that's the same amount each time. Now, is our y value then, as x decreases by the same amount, is y decreasing by the same amount or increasing by the same amount? Well, we're going from 3 to 2, so we're decreasing by 1. So this needs to decrease by 1 also in order to be a linear function, and it does. Therefore, this is a linear function. Here, I have a graph. That's all I have. So what I'm going to do is I'm going to use the vertical line test. I'm going to get my vertical straight edge and I'm going to move it across the graph from left to right. If I hit 2 points at the same time on my vertical line, this is not a function. So let's move it. Beep, 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 beep. Yes, we have 2 points here. We have 2 points here. We have an infinite amount of 2 points, right? Because the vertical line intersects the graph at 2 points at the same time, the graph is not a function. And I could have picked a number of points for this one.
Why did Mike Tyson break up with his girlfriend? Irreconcilable differences. That's a stretch. You try.
Okay, doing the same thing. Here we have our table, and in our table, we first determine, is it a function? Are there any x values that repeat? Yeah, 2 repeats. Because 2 repeats, this is not a function. So you just say, this table does not represent a function. Done. Next, is this a function? Do we have any x values that repeat? 0, 1, 2. No, no x values that repeat. Sweet, so we move to the next step. Is it linear or nonlinear? Well, x is increasing by 1 each time. Because x is increasing by the same amount, does y also increase by the same amount? Y is increasing by 3, and then by 4. No, in order to be a linear function, we would have to go from 3 to 6, and then from 6 to 9. Because we increase by 3 and then increase by 4, this would be a non-linear function. And then lastly, we have this set of ordered pairs, this relation that is graphed. In order to figure out whether this is a function first, we use our vertical line test, and we move it across the graph from left to right and see if this vertical line hits 2 points at the same time. And it does not. There are no repeated x values, therefore there are no points on top of each other. So this is a function. Now, is it linear or non-linear? Well, it looks to be forming a straight line. As you can see, as x increases by 1, y increases by 2. As x increases by 1, y increases by 2. As x increases by 1, y increases by 2. So therefore, yes, it is a linear function. Example 3 says for each table, determine whether the relationship is a linear function. Then represent the relationship using words, an equation, and a graph. So first, is this a linear function? Well, first, is it a function? Well, we don't see any x values that repeat. Therefore, yes, it is a function. Now, is it a linear function? Well, as x increases by 1, y increases by 1, then 3, then 5. Okay, because y is not increasing by the same amount each time, you can say that, no, this is not a linear function. This is a non-linear function. Next, relationship using words. We just said as x increases by 1, y increases by 1, then 3, then 5. Next, we need to represent our relationship using an equation. So it's going to be y equals, and then we have to figure out what are we doing to x to get y. Because it's nonlinear, we can't use the cheat codes that we used last time. The only thing we can do is the y-intercept. The y-intercept is going to be the same. It's 0, comma, and then whatever this is going to be our y-intercept. That's what we add at the end of our equation. So 0 is going to be added at the end of our equation, but that doesn't really help us. We have y equals, and now what are we doing to x to get y? Well, it's kind of looking like we square x, right? If I multiply x by itself, I get this, right? 0 times 0 is 0. 1 times 1 gives you 1. 2 times 2 gives you 4. 3 times 3 gives you 9. Therefore, we could say that y is actually equal to x, whatever x is, to the second power, x squared. And again, this checks out because for each of these x values, if I were to plug them in for x here and square them, I would get the corresponding y value on the other side of the t-table. Now let's go ahead and represent this relationship using a graph. So we're going to graph each of these points. Let's plot each of these points. 0, 0, that's our origin, so we put that right in the middle. 1, 1, we go over 1 on our x-axis, up 1 on our y-axis, put a point. 2, 4, we go over 2 on our x-axis, up 4 on our y-axis, put a point. 3, 9, we go over 3 on our x-axis, up 9 on our y-axis, put a point. You can see that, yes, this is a function because it passes the vertical line test. There's no x values that repeat, and it's non-linear, right? It looks like it's curving upward. It has an exponential curve. You can also see that our y-intercept is 0, and that's why we have nothing added or subtracted to the end of this equation.
What do Ronda Rousey and the Chicago Bears have in common? They both lost on the last kick. Oh, you try.
Okay, doing the same thing. First, is it a linear function? We have no x values that repeat, so yes, it's a function. Is it a linear function? Well, as x increases by 1 each time, y increases by 1, then by 7, then by 19? No, this would not be a linear function, it'd be a non-linear function. And we said the relationship using words as x increases by 1, y increases by 1, then 7, then 19. So now we have to describe this relationship using an equation. So it's going to be y equals, and then we're going to have to do something to x to get y. Well, think about what we did last time. We squared it to get our y value. Is there something that you see? Is there a pattern that you see? Is there something we could do to these x values to get these y values? Well, actually, it looks like I could cube these x values to get these y values. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. 3 to the third power, 3 cubed is 27. So yeah, our equation is going to be y equals x cubed, x to the third power. Now we can go ahead and graph each of these points. So 0, 0, that's our origin. 1, 1, we go over 1 on our x-axis, up 1 on our y-axis, put a point. 2, 8, we go over 2 on our x-axis, up 8 on our y-axis, and put a point. And then 3, 27 is obviously going to be somewhere way up here off our graph. So now you can see, yes, it is a function because we don't hit 2 points at the same time with our vertical line. It passes the vertical line test. And the graph is non-linear. It clearly is curving upward, has an exponential curve. And 0, 0, that is our y-intercept. And because it's our y-intercept, it's whatever's added or subtracted at the end of our equation. Since it's 0, there's nothing here. Example 4, doing the exact same thing. First, is it a linear function? Well, is it a function? Do we have any x values that repeat? No, so it's a function. Is it linear? Well, x increases by 1 each time, and as x increases by 1 each interval, you can see that y increases by 2, then increases by 2. Okay, that's a good sign. But then increases by 14? No, this is going to be a non-linear function. Next, let's describe the relationship using words we just did. As x increases by 1, y is increasing by 2, then by 2, then by 14. So now we have to describe this relationship using an equation. So it's going to be y equals, and then we're going to have to do something to x to get these y values. Well, it's not squaring them. What about x squared plus 1? Well, that would work here, right? This squared plus 1 gives you 2. What about this squared plus 1? No, that would be 1. So it's not that. How about this squared times 2? If I did 1 squared times 2, I would get 2. If I did 0 squared times 2, I would get 0. Negative 1 squared is 1 times 2 is positive 2, not negative 2. So that would not work. Interesting. What about 2 times x cubed? What's -1 cubed? That's -1 times -1 is +1 times -1 is -1 times 2 is -2. Okay. What's 0 cubed? 0 cubed is 0 times 2 is 0 still. What's 1 cubed? That's 1 times 2 is 2. What's 2 cubed? That's 8 times 2 is 16. We found something that works. Y is equal to 2 times x cubed. So to the third power. Now what we can do is we can graph each of these points. So -1, -2, we go over -1 on our x-axis, down -2 on our y-axis, put a point. 0, 0, that's our origin, we put a point there. And then 1, 2, we go over 1 on our x-axis, up 2 on our y-axis, put a point. And then 2, 16, we go over 2 and then up 16 somewhere. And you can see that, yes, it is a function. It passes the vertical line test, doesn't hit 2 points on our vertical line at the same time. And it is a non-linear function. This looks linear, but if you add this point in up here, it's clearly non-linear. Also note that our y-intercept, 0, 0, is here, and that checks out because there's nothing added or subtracted at the end. Therefore, that is going to be our y-intercept, 0.
You try!
Okay, doing the same thing. First, is it a function? Well, we have no x values that repeat, so yes, it's a function. Is it linear? Well, as x is increasing by 1 each time, y increases by 0.5, then 1.5, then 2.5. So no, it is a non-linear function. Next, relationship using words. As x increases by 1 each time, y increases by 0.5, 1.5, and 2.5. Next, our relationship using an equation. This is where it gets tough, okay? This is where it takes practice. You have to do a bunch of these in order to be able to see this pattern. So what I do, I always check if it's nonlinear. Let's try squaring it. If I were to square this, what's 1 squared? That's 1. So that's clearly not that. What about 1 squared divided by 2? Yeah, okay. 1 squared divided by 2 gives me 0.5. How about this? 2 squared is 4. Divided by 2 gives you 2. Yeah, sweet. 3 squared is 9. Divided by 2 gives you 4.5. Yeah, and 0 squared divided by 2 is still 0. Okay, so that's it. It's y is equal to, and we're going to do x squared, whatever x is, we're going to square it and then divide it by 2, or y equals 0.5 times x squared. And that works for each of these x values. Sweet. Now what I can do is I can graph each of these points. So 0, 0, I put at our origin. 1, 0.5, I go over 1 on our x-axis, up 0.5 on our y-axis, put a point. 2, 2, I go over 2 on our x-axis, up 2 on our y-axis, put a point. And then 3, 4.5, I go over 3 and up to 4.5 and put a point. And you can see clearly this is a function because it passes the vertical line test, and it's non-linear because it's clearly curved. Also note that our y-intercept, 0, 0, is still going to be whatever's added or subtracted at the end of our equation, as long as it's y equals. Okay, the word problem says the table shows the number of new branches a tree grows over the course of 4 months. What is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. So first, here's our table. This is the relationship using a table. As you can see, the independent variable, our x value, is going to be time in months. The dependent variable, our y value, is going to be the number of branches. So as our x value, as our time in months increases by 1, our number of branches increases by 6, and then by 18. What is a pattern that we can see? We go from 3 to 9 to 27. Now what's interesting about that? Well, 3 squared gives you 9, and 3 cubed gives you 27. What does 3 to the 4th power give you? Well, that gives you 81. Well, that seems right? If I have 3 to the 1st power, gives you 3. 3 to the 2nd power gives you 9. 3 to the 3rd power gives you 27. 3 to the 4th power then would give you 81. That would complete our table. Now, if we describe this relationship using words, we said as the number of months increases by 1, the number of branches increases by 6, by 18, and then by 54. Now, the relationship using an equation is going to be y equals, and how did we do this? We did whatever the number of months is, that's going to be our exponent for 3. So it was 3 to the 1st power, 3 to the 2nd power, 3 to the 3rd power, gives you your y value. So it's y equals, and it's going to be 3 to whatever the time is, to whatever our x value is. So 3 to the x power. Now what we can do is we can graph this, and our x value, our independent variable, is going to be the time in months, and our dependent variable is going to be the number of branches. So that's going to be on the y-axis. You can see here that it says the number of branches in tens. Okay, so we're going up by 10. So this is 10, 20, 30, 40, 50. Now let's graph each of these. 1, 3 then would be 1, and then 3 would be somewhere right here. 2, 9 then would be over 2 on our x-axis, up 9, almost to that 1 right here, because that represents 10. And then 3, 27 would be over 3 and up close to the 3 because that represents 30. And then 4, 81 would be over 4 on our x-axis and up a little bit above the 8. So that would be somewhere right here. And you can see that this is clearly a non-linear function. It's an exponential function, and we have successfully graphed each of these. The main takeaway from this, I don't expect you to right off the bat get this equation every single time. Right now, I just want you to do a bunch of them and start seeing certain patterns in these tables.